Hello, everyone. Welcome back. We are now going to continue with our long module 7, which is all about solution chemistry. We are going to look into precipitation reactions at the moment, so let's get started. All right. Precipitation reactions are reactions in which a solid forms. This is called the precipitate. And this, when a solid forms, when we mix two aqueous solution, by definition, I have a precipitation reactions. So these precipitation reactions occur when I have a reaction between aqueous solutions of ionic compounds that produce as a product an ionic compound that is insoluble in water. So this insoluble product will actually fall out of the solution because it's not soluble in the water, and then the solid is called a precipitate. Here's an example. I know that lead 2 nitrate is soluble, and I know this because it's got that nitrate ion, which is soluble with no exceptions. The potassium iodide is soluble, and I know that because it's a group 1 metal cation. When I react these two compounds, what I have is sort of a double switch. And what I get is potassium nitrate, which is soluble because it has a potassium salt, and I can stop right there because I know that would be soluble. And I also have a nitrate. And here, this is insoluble. This is that lead 2 iodide that's forming in the solution. It's a yellow solid that is precipitating out of the solution. And I know that iodides are generally soluble except for lead 2+. So this is going to form an insoluble compound. And again, let's look at it in sort of my molecular level. Here, my potassium iodide solution has got potassium plus cations and iodine minus anions dispersed throughout the solution because it's soluble. And then my other solution has lead 2 nitrates. The nitrate makes that soluble, and I have the lead 2+ ions and the nitrate ions dispersed throughout the solution. I mix those together, and again, I'm forming this yellow cloud of material. And actually what's happening is my potassium ions and my nitrate ions are still in solution, but now I'm forming this crystal lattice, which is that solid, insoluble lead 2 iodide. So I'm forming this crystalline material, which is falling out of solution and forming that yellow precipitate at the bottom of my Erlenmeyer flask. Precipitation reactions do not always occur when I have two dissolved ionic solutions and mix them together. For example, let's look at this reaction. If I take KCl, which is soluble, it's a group 1 metal, and I react it with NaCl, which is soluble, and anything that's soluble, I'm always going to use that AQ. Notice in that lead 2 iodide reaction, let me just scroll up again, this solid state is always going to be indicated when something does precipitate out of solution. But let's look at this guy again. When I combine them, the other potential products would be KCl and sodium iodine, both of which are soluble. So basically I get no reaction because nothing happens if I mix solutions of KCl and NaCl. All of my ions are just in solution. Nothing is recombining. I actually get kind of a mess. And this is defined as no reaction in because I do not form precipitates, and nothing else really happens either in this particular combination. So one task that you're going to have to be able to do for this class is to predict the products of precipitation reaction. To do this, I'm going to follow a procedure. It looks really long, but once you get the hang of it, honestly, you can just look at the reaction and figure out what's happening. But let's go through this procedure sort of step by step so that you understand fully what's going on when we try to predict the products of a precipitation reaction. The first thing I have to do is look at the two reactants, and I have to determine which ions are present in those aqueous solutions. Then I'm going to figure out what possible products can be formed. So I'm going to exchange the ions in my two reactants. The positive ion from one reactant gets recombined with the negative ion from the other reactant. This is really important. I have to balance the charges of those newly combined ions, and I have to write the correct formula of the potential products. This is where I use my nomenclature rules. If I don't have the right formula, I'm not going to get credit for this question. I must make the correct formula for the new combination of ions when they switch in this precipitation reaction. Once I get those new products, I need to determine the solubility of each of those new products in water. So I'm going to use the solubility rules. If the product is insoluble or just slightly soluble, it will form a precipitate. If neither product will precipitate, if both the new possible combinations are aqueous, are soluble in water, I'm going to write no reaction, and I can stop right there. If, however, I find out that any of the possible products are insoluble, I'm going to write their formulas as the product of the reaction. I'm going to indicate this solid state after the formula, because if it's forming a precipitate, it's forming a solid. Any soluble products that are formed, like in the other example I had potassium nitrate, which is soluble, I'm going to write the state AQ, because that indicates that it is soluble in the aqueous environment. I'm going to balance the total equation, and remember, I can only change coefficients and not my subscripts. I have to make sure that I write the correct formulas. This is a critical step. Here's an example of how we did that in the example we used before. I had lead or potassium iodide and lead 2 nitrate. So in potassium, I had the potassium ion and the iodide ion, and then I had the lead 2+ ion and 2 of the nitrate ions. So really I get 2 of those, and I don't have that subscript. This is based from this compound. And then I'm going to recombine. The lead combines with the iodine. Notice if I have Pb2+ and I-, right? This is my new combination. The correct formula to balance those charges is going to be PbI2. And then When I look at the other combination, my potassium and my nitrate, I have K plus and NO3 minus. That would be a 1-to-1 ratio and give me that possible product. So what I have is as the final result, I have my potassium nitrate and my lead iodide. This is going to be a solid, and this is going to be aqueous when I use those solubility rules. All right, so let's practice. And this would be 2, and this would be 3. Let's say I want to mix solutions of iron 2 sulfate. So iron 2, and then sulfate is SO4 minus 2. So I have FeSO4. And I want to look at my solubility rules to determine the state of this. So if I look at my solubility rules, I have all sulfates are soluble except for, and iron is not an exception, so this is going to be aqueous. And then I'm going to look at barium hydroxide. So barium is Ba2 plus and OH minus. So I'm going to have BaOH2. Hydroxides are not soluble except for when they're combined with barium 2 plus. So this is also soluble. Now, how am I going to do this predict the products? I'm going to look at iron and hydroxide, and I'm going to look at barium and sulfate. So when I look at the iron, now I have Fe2 plus and OH minus. So I'm going to have FeOH2. And then I'm going to have barium, which is Ba2 plus, and SO4 2 minus. So I get barium sulfate. And I want to check those states. Hydroxides are not soluble except for, this is actually going to be a solid. And then barium sulfate. Sulfates are soluble except for. So in this particular reaction, I formed 2 solids. And the last thing I'm going to do is check my balancing. 1 iron, 2 hydroxides, 2 hydroxides, 1 barium, 1 sulfate. I'm good. So this one's a little bit of a difference because I actually get these 2 solids in this particular example. You need to follow your solubility rules. Now, is this actually doable when I form 2 solids like this? It depends. I'd have to be able to separate them out. But you get the idea of how I'm going to go about this problem. So let's look at the next one. I have calcium chloride. Calcium is 2 plus, Cl is minus 1. So I have Cl, Cl2. All chlorides are soluble, and it's not an exception, so this is aqueous, plus potassium phosphate. Well, potassium is plus 1, phosphate is minus 3. So I have K3PO4, that's aqueous because I have potassium group 1 metal cation. Then, again, I'm going to look at this. Calcium and phosphate go together, and then potassium and chloride go together. So when I write the products, I have calcium 2 plus and phosphate 3 minus. So I'm going to get calcium 3, PO4 2. And then the other product I'm going to get is going to be the KCl. Potassium is +1, chlorine is -1. I know this is soluble because it's got a potassium cation. Phosphates. Phosphates are soluble or are insoluble except for group 1A metals and ammonium. So this is actually going to be my precipitate. This is going to be a solid. Now, is this balanced? No. I have to think about balancing it. So I'm going to need, let's start with the chlorine. Or the calcium. I'm going to need 3 calciums, which means I have 3 there, which means I have 6 chlorides, which means I put 6 there. And I have 2 phosphates. So if I put a 2 here, that gives me 6 potassiums, which is here. So 3 calciums, 6 chlorides. 3 calciums, 6 chlorides. 6 potassiums, 2 phosphates. This would be the balanced reaction. This is what I'm going to write in my predicted products. Let's do another one. What if I have calcium nitrate? Calcium is +2. Nitrate is going to be NO3 minus. So I have Ca, NO3, 2, and that's going to be aqueous because it's a nitrate salt. And then I'm going to use sodium chloride, which is aqueous because it's a sodium salt. Now, when I combine these, I'm going to combine calcium with chlorine. So that would be CaCl2. And then I would combine sodium with nitrate, which is NaNO3. This is aqueous. Calcium chloride is also aqueous. So this is no reaction, and I don't have to worry about balancing or anything else. I'm done at the moment. Now, there are different ways that I can represent these aqueous reactions. I can use a molecular equation, which is what we're used to seeing. That's what I have been writing. I'm going to write all substances in the chemical equation as their complete formulas as if they were molecules. So I'm going to use their complete formulas as if they were molecules. So this is going to be my molecular equation. Notice my soluble lead-2 nitrate and my soluble potassium iodide and my soluble potential product, which is potassium nitrate, are all considered to be strong electrolytes because they're soluble ionic compounds. Lead-2 iodide is my precipitate, and I'm going to make sure that I represent that as my solid. When this is balanced, this is giving me the molecular equation. I could also have the ionic equation. This is also the complete ionic equation, where all of the strong electrolytes are going to be written as ions. So my lead nitrate, my lead-2 nitrate is going, and I'm going to pay attention to the stoichiometry here. So this is going to dissociate into one lead-2 plus ion, aqueous, and 2 nitrate ions, aqueous. My potassium iodide is going to dissociate into, because I have this coefficient here, I get 2 potassium plus ions, aqueous, and 2, remember this is sort of like the distributive property, 2 I minus ions. Now on the product side, this is a solid, so that stays intact. Only the strong electrolytes are going to be written as ions. Anything that's a solid, a liquid, or a gas is going, or an insoluble substance, right, is going to be written as this solid, and it's going to stay intact. So my product is 2 nitrates, or 2 potassium nitrates, so that dissociates into 2 potassium plus ions and 2 nitrate ions. So this is the complete ionic equation, where I write all of the ions that are in solution and the products. The product that is remaining in solution, if there is one, is broken up into its ions, and the product that is the precipitate is going to remain intact as the solid. Now, let's consider spectator ions. Spectator ions, think about what a spectator does. If I'm a spectator and I go to a baseball game, I'm watching what's going on, but I'm not actually participating. So spectator ions are ions that undergo no change. They just hang around and watch during the reaction. These ions will appear on both sides of the reaction arrow, and they won't be changed. So if I look at my complete ionic equation for this reaction, I notice I have 2 nitrates and 2 potassiums, and I have 2 potassiums and I have 2 nitrates. The thing that does change is lead-2 plus reacts with those 2 I minuses and forms this lead-2 iodide. But before and after the reaction, I have 2 potassium ions that are unchanged and 2 nitrate ions. So basically, what I'm going to do is characterize these as spectator ions, and they can actually cancel out of the reaction just like we do in an equal sign and a mathematical equation. And what I'm left with is going to be something called the net ionic equation, where I show only the ions that are actually undergoing change. So the net ionic reaction for this particular reaction is lead-2 plus reacting with 2 I minus to form the lead-2 iodide. And again, if I cancel out my spectators, what I'm left with is the lead-2 plus and the 2 I minus forming that lead-2 iodide, which is what I'm representing here in my net ionic equation. So here's an example. Write the molecular, ionic, and net ionic equations when aqueous solutions of silver nitrate and sodium carbonate are mixed. So let's look at this. The first thing I'm going to do is I'm going to write the chemical formulas of the products, and I'm going to use those proper ionic rules. The silver is going to combine with the carbonate, the sodium is going to combine with the nitrate. This is a double displacement reaction, so A and C switch. A are those 2, is the cation here. C is the cation there. They're going to switch, and I'm going to recombine. So what I get then, since silver is always +1 and carbonate is -2, I have to write this as Ag2CO3. And then remember, I have sodium plus and NO3 minus. So these are the two potential products that I would get when I recombine these ions. The molecular equation is going to be after I write everything down and I balance everything. I'm going to look at my solubility rules. I find out that silver carbonate is the solid. So this is my precipitate. And then sodium nitrate is going to be remaining in aqueous because it contains a group 1A cation. So I know that this is a solid. This is how I write my molecular equation, as if everything was a molecule, and then I'm going to balance. So I need this 2 here and this 2 there in order to balance all my atoms. And then this itself is going to be the molecular equation. If I want the ionic equations, anything that is a strong electrolyte are going to be dissociated. So my silver nitrate gets dissociated, notice my coefficient, to 2 silver plus 2 nitrates. Also represent the state, which is aqueous. My sodium carbonate, right? I'm going to get 2 sodium ions and 1 carbonate ion, both in solution. And then this is going to be a solid because it is insoluble according to the solubility rules. This is my precipitate. And then I have my 2 sodium ions and my 2 nitrate ions. Well, let's identify the spectator ions. On both sides of the reaction, I have the 2 sodium ions. And I also have the 2 nitrate ions. So my sodium and my nitrate ions are going to be spectator ions. When I think about canceling them out on both sides, what I'm now left with is going to be my silver plus my carbonate going to my silver carbonate. So this is going to be my net ionic equation that I write here. I cancel out my spectator ions, right? I eliminate the spectator ions, and I'm just representing the ions that actually change. And this also needs to be balanced. So if you balance that molecular equation, and I follow the fact that for 2 silver nitrates, I get 2 silver and 2 nitrate ions, this will be balanced at this time as well. So let's practice. Does a precipitate form when sodium chloride is mixed with silver nitrate? If so, write the net ionic equation for the formation of the precipitate. Sodium chloride, Na plus, Cl minus, I have NaCl. That's going to be aqueous because it's a sodium salt. Silver nitrate, Ag plus, NO3 minus. So I'm going to have AgNO3. That's also going to be aqueous because of a nitrate ion. The solutions, or the ions in solution, I'm going to combine sodium nitrate with the silver chloride. So if I get NaNO3, that will be aqueous because it's a sodium ion, group 1A, and it's a nitrate. And then the other potential product is silver chloride. Now this is a precipitate because we learned in the beginning that chlorides are soluble generally, but when I have a silver salt, then this is going to be insoluble. This is my molecular equation right here. So let's look at if it's balanced. Everything is 1 to 1 to 1 to 1, so it is balanced. So this is the molecular equation. If I want to write the complete ionic, I'm going to break this up. Sodium plus aqueous plus Cl minus aqueous plus Ag plus aqueous plus NO3 minus aqueous goes to, I'm going to break sodium nitrate up, Na plus aqueous plus NO3 minus aqueous. This is my precipitate, so it stays intact, AgCl solid. So notice I have spectator ions. My sodium is unchanged on both sides. My nitrate is unchanged on both sides. So again, those can cancel out. And then what I'm left with is my net ionic, which is going to be silver plus. I don't have to write this in this order, but I almost always put the cation first just by convention. Plus Cl minus aqueous goes to AgCl solid. And that would be the net ionic equation. Here's another example. If I have sodium chloride, which is aqueous, and I mix that, oops, this is the same thing. So let's do this practice. Sometimes I have these doubles in my slides, which drive me crazy, but at least I figured that out. Anyway, let's do this one. What if I have an aqueous solution of aluminum chloride? So let's look at this. Al3 plus, Cl minus. So my correct formula is going to be AlCl3 aqueous. I want to check that one. All chlorides are soluble except for aluminum is not an exception, so that is in fact aqueous. And then I have sodium and I have hydroxide. So I have NaOH. Is that soluble? Yes, because it's sodium plus, which is a group 1A cation. Then I'm going to go ahead and switch them. I'm going to get NaCl, which is in fact aqueous. And then I have to combine aluminum 3 plus and hydroxide. So I get AlOH3. Hydroxides are insoluble except for aluminum is not an exception, so this is going to be my solid precipitate. Is this balanced? No. So how am I going to balance it? I'm going to look at what is a quick fix. I have 3 chlorines here and only 1 here, so I'm going to put 3 there. That gives me 3 sodiums, so I need a 3 here. And then, am I balanced? Yeah, so I have 1 aluminum, 1 aluminum, 3 chlorines, 3 chlorines, 3 sodiums, 3 sodiums, 3 hydroxides, 3 hydroxide. So this is my molecular equation. What about complete ionic? Well, I'm going to have Al3 plus. Notice in my complete ionic, I must have the ion charges, and I also need to put that AQ state. Plus 3, notice I'm using that subscript because each molecule, each formula unit of aluminum chloride will give me 3 Cl minuses, which are aqueous, plus 3 Na pluses, which are aqueous, plus 3 OH minuses, which are aqueous. And then on this side, I'm gonna break up the sodium chloride, 3 Na plus, which is aqueous, plus 3 Cl minus, which is aqueous, plus, I'm going to keep my precipitate together, AlOH3, solid remains together. So this is my complete ionic. Again, what is actually reacting and what is hanging around looking at me? My sodium is a spectator ion. My chlorine is a spectator ion. So they're all going to cancel. And for my net ionic, what I'm going to get is Al 3 plus aqueous plus 3 OH minus aqueous goes to AlOH3 solid. Hopefully you're getting the hang of this as you do more and more of these products. I'm not going to do all these. I think you get an idea. But this is a great little set of problems that you should look at. See if you can predict the products, predict whether a precipitation reaction will take place, then write the molecular, the complete ionic, and the net ionic, and identify the spectator ions. This is what you might see on an exam, and this is also what you're going to do in that chemical reactions lab report, where you're going to be looking at combinations of compounds and predicting whether they're going to react. Now, in those labs, we look at other types of reactions, not just precipitation reactions. We also look at acid-base reactions, and we look at gas evolving equations, which are what we're going to talk about next as we continue to go through Module 7. So that's it for now. I will see you in a little bit to continue our discussion on other types of aqueous reactions. I'll see ya.